Spin a pile of rocks fast enough, and the pieces fly apart. That's gravity losing to centrifugal force, the same physics that makes a washing machine walk across the floor when it's unbalanced by a single sock. Now make that pile 710 meters wide. Spin it once every 1 minute and 53 seconds. It should shred itself into a slow grey cloud in space. Instead, it holds together, whole, spinning, refusing to fall apart. This object is real. It's called 2025 MN45, and it completes a full turn faster than any object of its size ever recorded. It should not exist in one piece. And it does. Here's the part that should bother you more than it probably does. The telescope that found it wasn't even trying. It was running a 10-hour test, warming up before its real 10-year mission had even begun. In 10 hours, it flagged over 2,000 objects nobody had ever catalogued before. And buried inside that pile was the one rock that shouldn't be there at all. Convenient, isn't it? That the very first thing a machine like this sees is something that shouldn't survive its own physics. An accident that keeps passing the engineering review. The machine is the Vera C Rubin Observatory, high in the Andes on a peak called Cerro Pachon in Chile. It doesn't look like a traditional telescope. It looks like a fortress built to catch light. Its primary mirror is 27 feet across, and it wasn't poured into a mold. It was baked in a spinning oven built underneath a football stadium at the University of Arizona. Molten glass spun for months, so centrifugal force could shape a flawless curve. We spent $20 million spinning glass in a stadium just to build a lens sharp enough to realize we had no idea what we were looking at. Inside sits a camera the size of a small car, 3 tons, 3.2 billion pixels. To display a single one of its images at full resolution, you'd need nearly 400 ultra-high-definition screens. But the real power of this machine isn't its size. It's its speed. About every 40 seconds it takes an enormous new image of the sky. Then it does something more important than photography. It compares now with before. A dot moved, a star brightened, something appeared, something vanished. For the entire history of astronomy, we've been taking photographs, a single frozen frame over and over. Now we're filming a movie. And the sky is not polite enough to remain still between frames. Asteroids move, stars explode, galaxies brighten. In a single night, this machine can generate millions of change alerts, millions of ways for the universe to say, something just happened. For centuries, we missed the fast stuff. We missed the transients. A transient is anything in the sky that changes, flashes, or moves. Take a photograph of a busy highway, with your shutter open for a microsecond, and you'd conclude the road is a quiet, static place. Film it, and you see the violence, cars weaving, trucks braking, headlights flashing. That's what Rubin is seeing now all over the sky. Calling the sky static was never really an observation. It was a limitation of how often we could look. When your instrument improves, nature doesn't change. Your excuses do. So back to the spinning rock, because it forces the real question. What keeps a pile of rubble from becoming, well, a pile of rubble? The answer is almost embarrassing in how ordinary it sounds. Gravity and a weak electrostatic stickiness between grains of dust, the same clingy static that makes a balloon stick to your hair. That's the glue holding a football field-sized object together against a spin that should shred it. Weak forces doing heavyweight work. But stretch this further, because the asteroid is just the visible symptom. Large asteroids that behave like loose rubble piles have a problem. Spin them too fast, and gravity can't hold them together. For most of them, the familiar spin barrier sits around 2.2 hours. 2 hours. MN45 spins in less than 2 minutes. Roughly 70 times faster. That's not a rock being stubborn. That's a rule being broken, and the rock didn't get the memo that it was supposed to be the exception. Now zoom out, because this isn't about one asteroid. It's about cohesion, the tendency of matter to stick to itself instead of flying apart. Sitting at exactly the strength it needs to be everywhere, all the time. Too weak, and nothing holds together long enough to become anything. No planets, no rocks, no you. Too strong, and everything clumps instantly into dead, useless lumps, and chemistry never gets the freedom to build anything interesting. The rock spinning in the dark isn't an exception. It's the rule, caught in the act, under maximum stress. And the precision doesn't stop at rocks. Gravity is roughly a trillion times weaker than the electromagnetic force. Make it a little stronger, and stars burn through their fuel in a flash and collapse before life ever gets a foothold. A little weaker, and matter never clumps into stars at all. The strong nuclear force, the one gluing atomic nuclei together, turn that knob a couple of percent in either direction, and carbon, the backbone of every living thing, either never forms or falls apart the instant it does. Then there's the biggest dial of all. Physicists measuring how fast the universe expands have to account for a number called the cosmological constant, a value so precisely balanced that if it were off by 1 part in 10 followed by 120 zeros, the universe would have either collapsed back on itself in an instant or blown apart too fast for a single galaxy to form. That's not a small dial. That's a combination lock with more digits than there are atoms in every star you can see, opened correctly on the very first try, with no second attempt allowed, because a wrong guess ends the universe before it starts. Randomness, apparently, took the engineering exam, and aced it, without studying. Now watch what happens when humans try to master forces like this, with unlimited funding and our smartest minds in the room. CERN spent billions of dollars and decades digging a 17-mile tunnel under Switzerland, chilling magnets colder than deep space just to smash a few protons together and glimpse, for a billionth of a second, forces the universe produces constantly, for free, with no funding committee. NASA's DART mission spent over $300 million, years of planning, and an entire spacecraft just to nudge one asteroid's orbit by a few minutes, a controlled experiment to learn how rubble piles respond to force. Meanwhile, 2025 MN45, no mission, no funding, no review board, has been surviving in the vacuum of space for longer than humans have existed, using forces so weak we call them background noise. Billion-dollar labs straining for what a rock does by accident. Take the brightest minds at MIT, Harvard, and the Max Planck Institute. Give them the most powerful supercomputers on the planet. A few years ago, they built the illustrious project, an attempt to mathematically simulate just a small chunk of the universe. It took tens of thousands of processors running at full capacity, burning through colossal amounts of electricity just to render a tiny fraction of cosmic time without the whole thing crashing. The fans screamed. The servers overheated. Human engineering pushed to its absolute breaking point to build a cartoon of the sky. Meanwhile, the actual universe runs 2 trillion galaxies in real time, never overheating, never buffering, never dropping a single frame. We call it a coincidence because the alternative is a word the textbook isn't allowed to print. We can no longer pretend the sky is a quiet painting. The movie is playing, and we finally pressed record. Every star, every rogue planet, every invisible thread of gravity is hitting its mark night after night, across 14 billion light-years of cold, unforgiving dark. We started with a spinning rock. That led to the glue holding rubble together. That led to the exact strength of every fundamental force in the universe, each one sitting inside a range so narrow that one wrong digit ends everything. And every layer we peel back opens into a bigger one, and every layer passes the same impossible test. For something with no plan, it shows up oddly often. The telescope isn't uncovering an exception. It's opening a filing cabinet of the same exception over and over on schedule. So ask the only question left standing. How much precision can we keep calling accidental before the word stops explaining anything? Who calibrated this, if no one was there to calibrate it?